Hello, and welcome to the Cosmic Whisper. I'm truly glad you're here. Maybe you've had a long day, or your thoughts are still gently spinning like satellites. Maybe you're just someone who finds comfort in quiet questions. Wherever you are, whatever time it is, this moment is just for you, a little corner of calm carved out in a busy world. So take a breath, settle in. You don't have to do anything now. Just listen, just drift. Tonight, we'll go on a gentle journey through something strange and beautiful, something that touches everything you've ever seen but moves too fast for you to feel. We're going to talk about light, but not in the way school books did. No equations, no pressure to understand, just a soft, slow unfolding of wonder. Light, it fills our homes. It lets us see faces we love. It dances across the water at sunset, and it travels across galaxies to show us stars that burned out before we were born. It's always there, flickering behind every color, every screen, every reflection. But how well do we really know it? We think of light as simple. Flip a switch and the room glows. Step outside and the sun wraps everything in gold. But light is one of the strangest things in the universe. It moves without mass. It carries no time inside it. And of all the speeds anything can go, light seems to have chosen one, and never, ever changes it. Why? Why does light, this soft, flickering companion of life, have a speed limit? It's a question that seems innocent, even dreamy. And yet, tucked inside it are secrets that bend space and twist time. The answer isn't just scientific. It's poetic. It's fundamental. It's everywhere. But we're not rushing to that answer tonight. No, we're going to drift toward it slowly, like light itself moving through the darkness. For now, just feel it, that quiet rhythm, that stillness wrapped in motion. You don't have to solve anything. You don't need to stay awake for every word. Let your thoughts float if they want to. Let your breath slow. Let the glow of curiosity guide you gently forward. Because sometimes the biggest truths don't arrive like thunder. Sometimes they arrive like light, soft, constant, and always on time. Light is one of those things that feels familiar until you really try to explain it. You see it every day. It shows you the faces you love, helps flowers bloom, lets your eyes find comfort in the morning. But what is it really? What is this gentle visitor that touches everything and weighs nothing? Let's begin slowly. Light is made of tiny things called photons. Think of them as little messengers, not made of matter like marbles or dust, but something quieter. Packets of pure energy with no mass, no rest, and no destination other than forward. They don't sit still. They don't pause. From the moment they are born, they move, and they move at one speed, a speed that never changes, no matter what. But photons aren't just particles. They're also waves. Not waves on the ocean, not something you can surf or scoop with your hands. These are electromagnetic waves, ripples in invisible fields, vibrating in perfect rhythm. One part electric, one part magnetic. These two fields dance together through space, always at right angles to each other, always in motion. No medium is needed, no air, no water, just space itself and their dance. Imagine it, a wave without an ocean, a particle that isn't solid, a travel with no weight, no clock, no resting place. It's hard to hold on to, even in your mind. That's why light feels so magical. It doesn't behave like anything else we know. It doesn't quite make sense. And yet it works. It moves through the universe, bouncing off mirrors, slipping through glass, and bringing us color, warmth, and life. Light is also strange because it doesn't age. If you could somehow become a photon, your experience of time would be nothing. From your point of view, you'd be born and arrive at your destination in the same moment. No waiting, no in-between. But from our perspective, we watch light take its time. 8 minutes to reach us from the sun, billions of years to cross the universe from distant galaxies. Light is timeless, yet it's our way of marking time. And still, there's more. Every beam of light is made up of countless photons, each carrying a sliver of energy, each part a great, silent river flowing from star to eye, from flame to face. The color of the light depends on how fast the wave vibrates. Slow and long, and you get red, warm and steady. fast and short, and you get violet, bright and sharp. But all of it, every hue and flicker, is just vibration, just movement through the void. This is a strange truth we begin with, that light is not a thing you can hold, and yet it holds the world together. It is not a sound, but it hums through space with rhythm. It is not a substance, but it carries energy across the cosmos, whispering between stars and eyes and leaves. It is particle and wave, messenger and dance, always moving, always constant. And so we begin to see just how curious this light really is, not just for what it shows us, but for what it is. It has no mass, but it can push. It carries no time, but it reveals history. It is simple enough to light a candle, and strange enough to bend the laws of space and time. Whatever light is, it's more than just brightness. It's a question, one that has followed humanity from the first fire to the farthest star. And now, it follows us gently into the next chapter, like a ripple in space, asking, if this is how light moves, then why must it move at only one speed? Light moves in a way nothing else does. Most waves need something to ripple through. Sound needs air. Ocean waves need water. But light needs nothing. It moves through emptiness with no hesitation, through the vacuum of space, across the great silent stretches between stars and planets. Light simply travels, not drifting, not coasting, but moving with quiet purpose. It doesn't lose speed, doesn't run out of breath. It just goes. That's what makes light different. It doesn't need a road. It is the road. Even when there's nothing, no particles, no breeze, no fabric to push against, light carries itself. It moves at nearly 300,000 kilometers per second. That's fast enough to circle Earth 7 times in a single second. And yet, somehow, it does so with grace. No rushing, no chaos, just steady rhythm. But light isn't just one kind of thing. What we call light is only a sliver of what's really out there. It belongs to a family, a vast, invisible spectrum of electromagnetic waves. Imagine a piano that stretches for miles. The notes we can hear, that's visible light. Just a few keys in the middle. The rest, the deep bass notes and the high, sharp whistles, we can't see. On the long end of the spectrum, there are radio waves. These are huge, rolling waves, sometimes as long as buildings. They pass through walls, bounce off the atmosphere, and carry music into your car. Then come microwaves, the ones that warm your food and let your phone talk to cell towers. After that, we find infrared waves, the gentle warmth you feel from sunlight or a cozy heater. In the narrow, colorful band we call visible light. Every color has its own wavelength. Red has the longest, most relaxed wave. Violet has the shortest, the most energetic. But beyond violet, the spectrum continues. There's ultraviolet, which gives you sunburns. Then come X-rays, which pass through your skin but stop at your bones. And at the far, intense edge are gamma rays, the most energetic, most dangerous waves, born in the hearts of dying stars and nuclear reactions. All of these are light. All of them travel at the same speed in a vacuum. What separates them is frequency, wavelength, and the kind of energy they carry. Some can slip through walls. Some can see through flesh. Some bring color to a painting. Others reveal galaxies billions of years old. But when light meets matter, its journey changes. It bends. It scatters. It slows down. Not because it's tired, but because the atoms in glass or water or diamond interact with it, absorb it, and re-emit it in tiny stutters. This delay makes it look like light is moving more slowly, even though each photon still races ahead at its usual speed between interactions. This slowing creates beautiful effects. A straw in a glass of water looks bent. A diamond sparkles because it bends and splits light so dramatically. A raindrop breaks sunlight into a rainbow. This bending is called refraction, and it's one of the quiet tricks light plays with the world. Light can also scatter. That's why the sky is blue. Shorter blue wavelengths bounce more in the atmosphere than red ones. It's why sunsets are orange and pink. The blue is scattered away, and we're left with the lower, warmer tones. Even the twinkle of stars isn't a star itself. It's Earth's atmosphere playing with the light, bending and shifting it as it reaches your eye. Everywhere light goes, it tells a story. Not in words, but in color, shape, and movement. It travels across space, touches planets, slips through leaves, bounces off oceans. It enters your eyes and becomes sight. It reflects off memories, illuminates dreams, dances across skin and stone. And always, it moves with the same rhythm. No matter how far it's traveled or what it's passed through, light continues, not changing its pace, not forgetting its path. Just one photon after another, weaving the universe together. This journey from one side of the cosmos to the other is not just a line, it's a lifeline. It's how we see the past. It's how we measure the stars. And it's how we know, even in the dark, that something beautiful is on its way. When we look around, we see color everywhere. The deep blue of the sky, the golden warmth of the sunset, the green of leaves catching the morning sun. But what if none of those colors actually exist outside your mind? What if color is not in the world, but in you? This is one of the quiet wonders of light. Color is not a property of objects. It's a story your brain tells when light reaches your eyes. Every beam of visible light carries a wavelength, a signature frequency of vibration. Long waves create red, shorter ones violet, and everything else, orange, yellow, green, blue, sits in between. But the apple isn't red. It's simply reflecting wavelengths that we interpret as red. Your eye catches those vibrations, and your brain paints the apple. Inside your eyes, on the surface of the retina, are special cells called cones. These cones are tuned to different parts of the spectrum. One kind responds best to long waves, reds, another to medium waves, greens, and a third to short waves, blues. Together, they create a kind of internal color code. Light enters your eye, strikes these cells, and each cone sends its signal. The brain then takes that information and weaves it into what you see. A red apple, a purple flower, a turquoise sky. But this process is not perfect. It's full of assumptions, shortcuts, and illusions. The same color can look different in different light. Shadows can make white seem blue. A bright red under streetlights may look brown. Your brain doesn't just read light. It interprets it, guesses at it, and sometimes fills in what isn't even there. This is why you can be tricked. Why one dress can look white and gold to some and blue and black to others. Your brain is doing its best with the data it's given. It doesn't see light directly, it translates it. And sometimes that translation bends the truth. The world you see is shaped by this process. It's personal, subjective, unique. No one else sees exactly what you do. Even if we agree on the name of a color, the way it feels in your mind may be entirely different from mine. Color becomes not just a signal, but a sensation. And then there are creatures who see what we cannot. Bees see ultraviolet patterns on flowers, hidden maps that guide them to nectar. Some shrimp can see far more colors than we can even imagine, with cones tuned to strange wavelengths. To them, the world is painted in a palette we'll never know. Their experience of light is something utterly alien, yet just as real. All of this comes from photons, tiny packets of energy vibrating across space. They don't carry color. They carry energy. The color happens later, inside the eye, inside the mind. It's a quiet act of translation, turning frequency into feeling. Even darkness isn't what it seems. What we call black isn't the absence of all light. It's the absence of light we can see. Infrared is still there. Radio waves pass through. The room might feel dark to your eyes, but it's still full of invisible light, quietly moving around you. And so, we live in a world built not of things, but of perceptions, of light bouncing, bending, reflecting, and minds interpreting those reflections into shape and hue. We see the world not as it is, but as our brains allow us to. Light, then, is more than just illumination. It is a carrier of experience. It brings form to the formless, color to the blank. It allows us to recognize a friend's smile, to read words on a page, to watch the sunset and feel something shift inside. All of it, every shadow, every sparkle, every shade of blue, is born from light's journey and the brain's quiet decoding. There is no red in the apple, no green in the leaf. There is only light and the way it dances with us. Long before lasers and satellites, before lenses and formulas, There were only eyes, stars, and questions. The first humans who looked up at the night sky didn't know what light was, but they felt its presence. Firelight flickering on cave walls, sunlight warming the skin, moonlight guiding the way through darkness. Light was a mystery, but it was also a comfort. It arrived without explanation, and no one thought to ask if it took time to get here. To most ancient minds, light didn't travel. It just was. You lit a flame, and the room was lit. The sun rose, and the world turned gold. Instantaneous. Obvious. Why would anyone think otherwise? But in the 5th century BCE, a Greek philosopher named Empedocles suggested something different, something strange. He believed that light might actually move, that it might take time to reach us. He imagined light as something emitted by the eye, stretching out to touch the world. It was a radical thought, and one that few took seriously. Most philosophers, including the influential Aristotle, dismissed it. They believed light was instant, a quality of the ether, not something that moved. That idea stuck for centuries. Even as the world changed, as telescopes were invented and ships crossed oceans, the idea that light might have a speed seemed too odd, too unmeasurable. It wasn't until the 17th century that someone decided to test it. His name was Galileo. Always curious, always questioning. Galileo wanted to measure the speed of light. He didn't believe it was infinite. He thought maybe, just maybe, light had a speed like everything else. So he designed an experiment that was simple and brave and, in its way, poetic. Galileo and an assistant each held a lantern. They climbed 2 distant hilltops, separated by about a mile. Each lantern was covered, so no light could escape. Galileo would uncover his lantern, and the moment his assistant saw the light, he would uncover his own. Galileo would then time how long it took for the second light to appear. The idea was clever. If there was any delay, it might be due to light's travel time. But there was a problem. Light is fast. Too fast. The human reaction time, the time it takes to see something and respond, is far, far slower than the time it takes light to travel a mile. Galileo couldn't detect a delay. The second light appeared almost instantly. He concluded that if light had a speed, it was much too fast to measure with this method. Still, he had asked the question. He had tried, and that mattered, because once a question is asked, it doesn't go away. It waits. And decades later, in 1676, it found another curious mind. A Danish astronomer named Ole Romer wasn't trying to measure the speed of light. He was just studying Jupiter and its moon Io, carefully recording when Io disappeared behind Jupiter and when it reappeared. But he noticed something strange. The timing of these disappearances changed depending on the season. Sometimes Io was early. Sometimes it was late. Romer realized this had nothing to do with Io itself. It had to do with Earth's position in its orbit. When Earth was moving away from Jupiter, Io appeared later than expected. When Earth was moving toward it, Io appeared sooner. Why? Because the light from Io had farther or shorter to travel. The difference in distance caused a delay. Romer estimated that it took light about 22 minutes to cross the diameter of Earth's orbit. He didn't know the exact size of that orbit. His numbers weren't precise, but his conclusion was revolutionary. Light takes time. It has a speed, not infinite, not instant, just very, very fast. In that moment, the cosmos shifted. Light was no longer an immediate gift from the heavens. It was a traveler, a messenger on a journey, and we had just begun to understand how far it had come. Once old Romer showed the world that light takes time, the race to measure its exact speed quietly began. It wasn't a loud race, not like the roar of rockets or the flash of discovery. It was a patient one, a slow unfolding of cleverness and curiosity, passed gently from one thinker to the next. More than a century after Romer's observation of Jupiter's moons, a French physicist named Hippolyte Fizeau tried something daring. It was 1849, and science was shifting from stargazing to hands-on experiments. Fizeau set up a light source, a rotating toothed wheel, and a distant mirror several kilometers away. He shined a beam of light through the spinning wheel, aimed at the mirror. The light passed through one of the gaps between the teeth, bounced off the mirror, and returned. If the wheel spun slowly, The returning light would come back through the same gap and be seen. But if the wheel spun faster, the returning beam would hit a tooth instead, vanishing from view. By adjusting the speed of the wheel and the distance of the mirror, Fizeau could calculate the speed of the beam. And he did. His number, about 313,000 kilometers per second. Not perfect, but stunningly close. Then came Léon Foucault. In 1862, he replaced the toothed wheel with a rotating mirror, refining the precision. Instead of blocking the light, the mirror redirected it. As the mirror spun, the angle of reflection shifted ever so slightly. By measuring how far the reflected beam moved, Foucault could calculate the time delay and thus the speed. His result was a little slower than Fizeau's, about 298,000 kilometers per second. Closer still to what we now know is true. These weren't just experiments. They were acts of patience, of control, of watching tiny changes with enormous meaning. Each flicker of light on a distant wall was a whisper from the universe, and each scientist leaned in to listen. But it was Albert A. Michelson who turned these whispers into music. Born in 1852, Michelson had a mind for light and mirrors. He refined Foucault's methods with greater precision, longer distances, and more stable environments. Using long, straight tubes, mounted mirrors, and incredibly precise timing mechanisms, he measured how long it took light to travel to a mirror and back. He accounted for vibrations, temperature, even the flexing of the earth. Michelson's work was so elegant, so accurate, that it became the gold standard. His final result, 299,796 kilometers per second, astonishingly close to the modern value. In 1907, he became the first American to win the Nobel Prize in Physics, not for discovering light, but for measuring it with such grace and discipline. By the 20th century, new tools emerged: lasers, atomic clocks, interferometers. Light speed was pinned down with breathtaking precision. In 1983, the scientific world decided to flip the script. Instead of measuring the speed of light, they defined it. The meter, the very unit of distance, was redefined as the length light travels in exactly 1/299,792 for 58 of a second. Light speed had become so fundamental, so consistent, so trusted, that we built our measurements around it. From moons orbiting distant planets to mirrors spinning in quiet laboratories, the journey to measure light speed was never just about numbers. It was about listening to the universe with care, about watching how a beam of brightness dances, about trusting that somewhere in the silence between reflections, a deeper truth waits. And one by one, with mirrors and math and deep stillness, we found it. In the mid-1800s, long before quantum mechanics and particle colliders, a quiet revolution was unfolding, not in a lab or on a mountaintop, but on paper. A Scottish physicist named James Clerk Maxwell was stitching together everything known about electricity and magnetism into something new, something whole. He didn't start with light. He started with fields, how charges move, how magnets spin, how invisible forces shape the world. Maxwell didn't discover electricity or magnetism. That had been unfolding for decades. Faraday had shown how magnetic fields could generate electric currents. Others had shown how electric charges could create magnetic fields. But it was all separate, scattered. No one had seen the pattern hiding in plain sight. Maxwell did. In 1864, he wrote down 4 equations, just 4, that captured the entire behavior of electric and magnetic fields. The equations weren't just technically correct. They were beautiful. They revealed that these two forces, long thought distinct, were actually one, intertwined and inseparable. And tucked inside those equations, like a quiet heartbeat, was something astonishing. When Maxwell did the math, something unexpected appeared. The equations predicted a kind of wave, a disturbance in the electric and magnetic fields that could move through space. Not through wires, not through matter, but through empty space itself. A wave that needed no medium. One that could travel on its own, sustained by the interplay of fields. And when he calculated the speed of that wave, he got a number: 299,792,458 meters per second. That number wasn't chosen. It wasn't estimated. It fell out of the math, clean and precise. It matched Almost exactly the speed of light. This was more than coincidence. Maxwell realized what he was looking at. Light, this mysterious thing that lit up the world, was not separate from the laws of electricity and magnetism. It was a ripple in those fields. It was the wave his equations had predicted. Light wasn't just energy. It was a moving dance between electric and magnetic forces. A wave that needed no wire, no substance, just space, and a speed that emerged naturally from the very constants that defined those forces. This changed everything. It meant the speed of light wasn't an accident or a limit set by nature out of habit. It was a necessity, the product of deep structure, of the way the universe is built at its most fundamental level. Maxwell's discovery meant that light's speed wasn't just fast. It was foundational. It tied together electricity, magnetism, motion, and space itself. It hinted that the universe had a kind of inner symmetry, an order behind the chaos, a rhythm behind the noise. And it showed something else too, that the universe isn't arbitrary. Physics isn't just a list of rules. It's a woven pattern. When you tug at one thread, like the movement of charge, you feel the pull all the way across the fabric, in fields and waves and beams of light. From that point on, light was no longer just brightness. It was proof of unity, a ripple that connected equations to experience, math to meaning. Maxwell didn't live long enough to see the full consequences of his work. But those four equations, quiet and symmetrical, would become the foundation for everything that followed: radio, lasers, electromagnetism, even the theory of relativity, all from the realization that light is a wave born not from water or wind, but from the very structure of space itself, a wave that travels always at the same unchanging speed, not because it wants to, but because the universe allows no other way. In 1905, a young patent clerk in Switzerland quietly rewrote the laws of the universe. His name was Albert Einstein, and his theory of special relativity didn't just shift physics. It tilted the way we see reality itself. At the heart of it all was one strange, stubborn fact. The speed of light is always the same. No matter who you are, no matter how fast you're moving, no matter what direction you face. Light always travels at exactly 299,792,458 meters per second. Not more, not less. This idea doesn't sound like much until you try to apply it. In the everyday world, speeds add up. If you throw a ball from a moving car, the ball's speed is the speed of your throw plus the speed of the car. But Einstein showed that light doesn't work that way. If you shine a flashlight while speeding through space, someone watching from far away won't see the light moving faster. Everyone, everywhere, sees it moving at the same speed. That's not just weird. It's impossible, unless everything else about reality bends to make it true. And that's exactly what happens. To preserve the constancy of light speed, the universe changes its rules. It lets time slow down. It lets space contract. It lets the order of events shift depending on your perspective, not in theory. In reality, this is time dilation. The faster you move, the slower your clock ticks compared to someone standing still. Not just by illusion, but by actual measurement. Fly fast enough, and time bends for you. Live near the speed of light, and you might experience a few years while centuries pass elsewhere. Then there's length contraction. Objects moving near light speed appear shorter in the direction of motion. A spaceship flying past at incredible speed will look squeezed, compressed, narrower than when it's at rest. Again, not an illusion, a real measurable difference. And maybe the most mind-bending of all, the relativity of simultaneity. Two events that appear to happen at the same time for one person might happen at different times for someone else, depending on their motion. There's no universal now. The present becomes a local concept. Time and space stretch and twist to protect one sacred thing, the speed of light. This isn't just a mathematical curiosity. It has consequences. GPS satellites orbiting Earth move fast enough and sit far enough from Earth's gravity that they experience both special and general relativity. Their clocks tick differently than clocks on the ground. If we didn't account for those differences, your phone would tell you you're in the wrong city. But there's something even deeper here. A reason the universe defends its speed so fiercely. Light speed isn't just fast, it's a boundary, a cosmic speed limit. Nothing with mass can reach it. No signal can exceed it. And that boundary does something crucial. It protects causality. If information could travel faster than light, effects could happen before causes. You could see a star explode before it explodes. You could receive a message before it was sent. The entire logic of time would unravel. Paradoxes would bloom like weeds. But the universe is built to avoid that. The speed of light forms a kind of protective shell around every event. Only things within that shell, within the light cone, can influence or be influenced. Outside of it, no signal can reach. No cause can affect. The limit is more than just speed. It's a structure that keeps time flowing forward, keeps stories from folding into themselves. Einstein didn't invent this limit. He revealed it, showed how the universe had bent itself around it, reshaped itself to make it unbreakable. In doing so, he gave us a new picture of reality. Not a grid of fixed space and time, but a fluid fabric where motion warps time and gravity curves space. And through it all, one number remains unchanged. One speed is always the same. Light, the ultimate constant. The fastest thing there is, not just in practice, but in principle. Not because it needs to be, but because the universe cannot be any other way. Imagine standing in an open field at night, a match in your hand. You strike it, and a tiny flame flares to life. From that spark, light begins to radiate outward in every direction. Not instantly, but at a fixed pace. 299,792,458 meters per second. That expanding sphere of light defines a boundary. The furthest distance anything could be affected by what you just did. Nothing beyond that sphere can know the match was lit. Not yet. Maybe not ever. This boundary has a name. It's called a light cone, and it's one of the most quietly profound ideas in physics. It maps out not just space, but time. It tells you what parts of the universe you can influence, and what parts can influence you. It separates the possible from the impossible, the knowable from the unreachable. Imagine a match as a single event in space and time. The light cone shows everything that can be touched by that moment, now and in the future. It also shows everything that could have reached you before that moment, the past cone. But beyond those regions, there are places too far away or too early or too late, places that simply cannot connect with you. Not yet, not ever. And the reason is simple. Light is fast, but not infinitely fast. It takes time to move. Even the most urgent signals, the most brilliant beams, must obey the cosmic speed limit. Which means every point in space has its own private history, its own little neighborhood of influence, its own version of now. There is no single universal present, no shared clock ticking across the stars. The now you experience is yours. It includes only the things whose light has had time to reach you. Everything else is either already gone or hasn't arrived yet. The universe is stitched together not by simultaneity, but by light. And the threads stretch only so far. This makes every moment local, personal, not in a sentimental way, but in a physical one. Your world is bounded by how far light can travel. What you see in the night sky, the shimmer of stars, the glow of galaxies, isn't the universe as it is now. It's the universe as it was. You're looking into the past, one photon at a time. Even the sun, so close and familiar, is slightly behind. Its light takes about 8 minutes to reach us. The light from the nearest star takes more than 4 years. And the light from the farthest galaxies takes over 13 billion years to arrive. What you see is a memory, still unfolding, still drifting toward you across space. This delay doesn't just affect vision. It shapes causality. You cannot send a signal to someone faster than light will allow. You cannot know what's happening far away until light tells you. That slowness, that gentle limitation, is what keeps the universe ordered. It makes sure causes always precede effects. It keeps time flowing forward, and not in loops or tangles. It also means there's no such thing as instant communication. Every message, every image, every voice carried through space is delayed. Even on Earth, satellites sending signals around the planet introduce tiny delays, fractions of a second but measurable. On larger scales, like speaking to a spacecraft on Mars, those delays stretch into minutes. This is not a flaw. It's a design. The universe has chosen slowness over chaos, delay over paradox. In doing so, it has given us something beautiful: structure. Light cones are not just diagrams in textbooks. They are the silent architecture of reality. They define who can talk to who can affect what, and how stories can unfold. Inside a light cone, events are connected. Outside it, they are strangers. That boundary creates a rhythm, a shape to time. It gives meaning to before and after. It ensures that the match you strike now cannot set fire to something light years away, not until light arrives, and only if it ever does. So we live inside these cones one moment at a time, not trapped, but defined, not isolated, but guided. Every photon that reaches us is a message from within our cone, a signal that we're still part of the great, glowing web of cause and effect. And in that quiet structure, we find clarity. The universe doesn't rush. It speaks in delay and distance, in the careful unfolding of time. Not all at once, but moment by moment, cone by cone, light drawing the lines between what was, what is, and what might still be. For as long as we've known about the speed of light, we've wondered if it could be broken. After all, humans are drawn to boundaries, just to see if they might bend. We've broken the sound barrier. We've climbed Everest. We built machines that touch the edge of space. So naturally we ask, what if something could go faster than light? The answer, so far, is no. But the question is worth exploring, if only for the quiet beauty of its possibilities. Start with tachyons, hypothetical particles dreamed up in the margins of equations. Unlike everything we know, tachyons would always move faster than light. Not sometimes. Always. And just as ordinary particles can't reach the speed of light from below, tachyons could never slow down to it from above. They live on the other side of the boundary. But there's a problem. If tachyons existed, they could send information backwards in time. And that opens the door to paradox. You could receive a message before it was sent. You could warn your past self and undo the message entirely. Causality, this gentle thread that keeps events in order, would unravel. So far, no experiment has found a tachyon, and most physicists quietly file them away as mathematical curiosities rather than real entities. Then there's quantum entanglement. Two particles become linked in such a way that measuring one instantly affects the state of the other, no matter how far apart they are. Einstein called it spooky action at a distance. It feels like faster-than-light communication, but it isn't. That's because you can't control what result you get when you measure one of the entangled particles. You can't send a message with it. It's like flipping two identical coins on opposite sides of the galaxy and finding that they always land the same, but you can't choose heads or tails. There's a connection, yes, but no way to use it to outpace light. Next comes something more visual: Cherenkov radiation. Imagine a particle traveling through water faster than light can move through that water. Not faster than light in a vacuum, but faster than light in a medium. It creates a glow, a sort of optical shock wave, the light equivalent of a sonic boom. That eerie blue shimmer in a nuclear reactor, that's Cherenkov radiation. But it's not breaking the cosmic speed limit. It's just moving faster than the local limit set by the material. Light itself still holds a high ground. And then we enter the realm of science fiction: warp drives and wormholes. Concepts that stir the imagination. A warp drive, in theory, could compress space in front of a ship and expand it behind. The ship wouldn't move faster than light through space. It would carry its piece of space with it, like riding a wave. The math, surprisingly, works. But the energy required would be enormous, perhaps greater than the mass of an entire planet. And it would involve exotic matter, something we've never observed. Wormholes offer another route: shortcuts through space-time that connect distant points. In principle, you could step into one and emerge somewhere far away, faster than any light beam traveling the long road between. But wormholes, if they exist at all, would be wildly unstable. Holding one open might require negative energy, a strange and undefined substance. And again, paradoxes lurk. If you could travel faster than light, you might arrive before you left. Time would twist, and causality could collapse. All of these ideas, tachyons, entanglement, warp bubbles, wormholes, are born from the edge of knowledge. They are beautiful questions, rich with imagination, but so far, they remain in the realm of what if, and maybe that's not a disappointment. Maybe the speed of light isn't a barrier to break, but a foundation to build on. Its constancy gives the universe order. It defines what's possible and what's safe from paradox. It draws a clean line between before and after. It lets time move forward, not fold on itself. The universe doesn't waste energy making shortcuts. Instead, it writes its laws with clarity. Light speed isn't arbitrary. It's structural. It's the pace that keeps everything from collapsing into confusion. And so, we chase the edge, not to break it, but to understand it. To trace the limit not as a fence, but as a frame. A reminder that some things are fast, but not everything should be. Some boundaries are not there to block us, but to hold reality gently in place. Light is not just a distant concept, drifting through galaxies and dancing across the edge of black holes. It's here with you right now. It's in your home, in your pocket, in your eyes. The same laws that guide starlight also guide the world you touch every day. Light is a hidden companion, quiet, constant, and absolutely everywhere. Start with something small. Your phone. Every time you stream a video, check the weather, or send a message, you're riding on pulses of light. Fiber optic cables, long threads of glass thinner than hair, carry that light beneath oceans and cities. These cables don't just connect places, they connect people. And they do it at nearly the speed of light. Each flash, each burst of data, bends and reflects its way through the glass, arriving with barely a pause. You tap the screen, and light runs halfway across the planet to bring you an answer. Then there's GPS, the quiet guide behind every map and direction. It works by timing. Satellites orbiting Earth send out signals, each one carrying the precise moment it was sent. Your GPS receiver listens to those signals and uses the time it took each one to arrive to calculate your location. But those times are tiny, measured in nanoseconds. And because light is the fastest thing we know, its speed is the yardstick that makes the whole system work. Even your sense of sight is built on light's behavior. When you open your eyes, you're not seeing objects directly. You're seeing photons, tiny packets of light that have bounced off surfaces and entered your retina. There, they strike cells called rods and cones, which send electrical signals to your brain. Your brain then creates the image. It's not just that light shows you the world. It is the world, at least as you experience it. And it goes further still. Your Wi-Fi, your Bluetooth earbuds, the radio in your car, these are all forms of light. Not visible light, but electromagnetic waves. Longer wavelengths, lower energy, but still part of the same family. When you stream music or take a call, you're listening to the same phenomenon that paints the sky at dawn, just tuned to a different frequency. In your kitchen, the microwave oven turns light into warmth. Microwaves are just electromagnetic waves with wavelengths longer than infrared. They penetrate food and make water molecules jiggle. That jiggling creates heat. No flames, no stovetop, just light moving atoms around, one vibration at a time. Go to the doctor, and light follows. X-rays, a higher frequency form of light, pass through soft tissue but stop at bone, revealing hidden structures. Infrared is used to measure temperature, even through layers of clothing. Light helps us look inside without cutting, helps us see what eyes cannot. And then there's the simple candle, a flame burning in the dark, releasing photons that have traveled through space since the Big Bang. When you watch that flicker, you're seeing combustion, yes, but you're also seeing electrons fall into lower energy states, releasing light. It's the same process that powers the stars. The candle and the cosmos share language. This is how deeply embedded light is. It doesn't just let us see. It measures, communicates, heals, warms, guides. And always it moves with the same constant pace, never faster, never slower. That speed is the foundation of modern life. It defines how fast we can connect, how accurately we can navigate, how clearly we can see. Yet for all its presence, light never announces itself. It doesn't ask to be noticed. It doesn't make demands. It simply moves, carrying color, carrying energy, carrying information. The speed of light isn't just a number in a textbook. It's the pulse behind the scenes, the quiet engine of everyday life. And perhaps that's the most beautiful part, that something so vast, so cosmic, so foundational, could be so gentle, so woven into your routines that you forget it's even there. But it is. From the glow of your screen to the warmth of your tea, from the signal in the sky to the image in the mirror, light is always there, your hidden companion, quietly keeping time with the universe. Somewhere in the silence between galaxies, a photon drifts. It has been traveling for nearly 14 billion years, ever since the universe first became transparent. This ancient light, soft, faint, stretched by time itself, still moves, still carries a story. We call it the cosmic microwave background. But really, it's a whisper from the beginning, a message from the moment the universe exhaled its first breath. This light has never stopped. It weaves through space, brushing past stars and gas clouds, slipping silently through the solar system, until, finally, it lands. On a detector, on a screen, on us. And in that moment, the past becomes touchable, not as a memory, but as presence. Light doesn't just remember. It arrives. And in its arrival, we find rhythm. Light is the quiet pulse of the cosmos. It's how stars shine, how planets glow, how galaxies speak across unimaginable distances. It's also how leaves turn sunlight into sugar. In the green stillness of a tree, photons strike chlorophyll, setting off a chain of events that feeds forests, feeds animals, feeds us. Photosynthesis begins with a beam of light. So does dinner. But the connection goes deeper. The calcium in your bones, the carbon in your cells, the iron in your blood, none of it came from Earth. It came from stars, from furnaces so hot that atoms fuse into heavier elements, scattered into space by explosions. Those atoms floated for eons, joined clouds, formed suns, formed planets, formed you. And all of that history was carried by light. Every breath you take is linked to a photon. Every heartbeat is measured against light's rhythm. The light from your lamp, from your screen, from the moon above. Each photon follows the same rule, obeys the same speed, pulses with the same rhythm. It doesn't matter if it was born in a light bulb or a supernova. It moves the same. Always. And that sameness is a comfort. Because in a universe filled with change and chaos, light is constant. Its speed never varies. Its path may bend, its color may shift, but its pace is unwavering. It's how we define distance, time, motion. We don't just observe the speed of light. We build our reality on it. It becomes a lullaby, a soft hum in the background of everything. The way a quiet clock keeps time in a quiet room. Not loud, not distracting, just always there, always steady. And when you look up at the stars, you're not just seeing points of light. You're seeing old stories, some older than Earth, some already ended. Their light is still traveling, still arriving, still painting the sky. You're not just looking out, you're looking back. The night sky is a library of time, written in beams that never rest. You are, in a very real sense, made of light, forged by it, fed by it, shaped by it. And as you sit here listening, breathing, drifting, light is still moving. Around you, through you, carrying warmth, carrying color, carrying memory. And maybe that's enough. To know that you're not separate from the universe, but part of its rhythm. A rhythm shaped by photons. A rhythm that began at the beginning and hasn't stopped since. So rest now if you can. Let that rhythm carry you. Let the light move through you, soft and silent, like the last whisper of the cosmos. Still glowing, still here, still moving forward.